We start with this molecule here, and then we are asked to draw two resonance structures, and there are more than two, so I'll draw the other ones. But there are two that are best, that avoid having an open shell atom, and that was some of the feedback I left on these was if something was like very unstable, then, and you're only asked to draw two, while it's a valid resonance structure and you wouldn't be marked down for it, I think it's still helpful to consider the stability of the resonance structures and what's more likely to form. So when you see a pi bond, so we have a double bond here. Remember, that can resonate, lone pairs can resonate. We also have that negative charge, and that's a good indication that electrons might resonate to neutralize that atom, only if there are other electrons that can resonate as well. So the pi bond can go up to the oxygen. That's definitely more likely than the electrons going down to this carbon. Again, that is possible, but then you have two negative charges right next to each other. That's really unstable. So let's actually just draw it going up to the oxygen. And I'm going to keep this one out of the brackets because it is the least stable of the three that I'm going to draw. This was a very common structure, but I'll explain why it's less stable. Or maybe you already know. I'm just going to abbreviate this as a CH3. So here we have an open shell carbon here, so that has a positive charge. We have positive right next to negative, and the feedback I left if a student drew this structure was that having this open shell carbon is very unlikely when I know we just took these electrons away, but the other atom it's bonded to has electrons that it can donate, and so does this one. And so those are the two most stable resonance structures, other than this, where we have nitrogen sharing electrons in one of them, and then this carbon sharing electrons in the other. So to go from the one I just drew to the first one I'll put in brackets, we just take the carbon lone pair and make it a pi bond between those two carbons. So now we just have one atom that has a charge. No atoms are closed shell. You can double check all these charges, but all the other atoms are neutral. Just oxygen has a negative charge. And then to go from this one to the other option with all atoms closed shell. Nitrogen electrons can create a pi bond here. Then we have to break this one and send it back to that carbon. And then when students drew this, a common mistake was missing this charge on the on the nitrogen. When nitrogen has 4 bonds, it has a positive charge. Okay. And then when we evaluate stability, most stable is the second structure where we only have one formal charge. True for both of these. Both of these only have one formal charge and no open shell atoms. But in this one, the negative charge is on the oxygen, which is more stable because oxygen is more electronegative than carbon. Carbon has a negative charge here. So that makes this one, second one major. And then the most minor would be the open shell. The one I drew down in the bottom. But this would be second minor, I guess, like more stable than the minor, but less stable than the other two. And then the first one would be second major. Typically, you are just identifying the major and the minor, but I still wanted to explain depending on which ones you have, like if you only have these two, then this one is your minor. If you have these two, then this one's your minor. If you have these two, then that one's the minor. Okay. Any questions on the learning check? All right. We will go to our notes then. And in the video, I explained some more about naming. So, well, actually, yeah, I'm trying to remember. Yeah, this is the class where we did a lot of naming. So some of this is new. We did these first two learning checks in class last week. This is what I covered in the video. So essentially, if you have two of the same substituent, this molecule has two methyls. You still have to write both numbers. They could be the same number or different numbers. But you don't write methyl twice. You would write dimethyl instead of methyl twice. And then if it's a ring, we just add the word cyclo in front of the parent chain, the longest carbon chain. So those are some examples there. So let's just take a few minutes to work on the remaining learning checks here. So there's two molecules at the top. There is a name right here, 3-chloro-4-tert-butyl hexane. So you want to look for that tert-butyl group on the previous slide. And then these three at the bottom as well. So I'll give you all a few minutes to get started. Let me know what questions you have, and we can go through them one at a time or all of them in a few minutes. We'll see what works best for us. Or are you just staying this one instead? I just have it early. Cool day. Yeah, it is. That's true. Okay. The Tues last week we got that. And if you have questions. Yeah, okay, that's your full longest carbon chain. And then on that. So, wait, which one are you working on? Because this one's actually. Well, part of that is part of hexane. So, yeah, so the 6 carbon. Okay, I'll start going through these examples on the bottom of the page. First molecule, the longest carbon chain is pretty apparent the way that it's drawn. Notice that if you happen to highlight, or when you're looking at the longest chain, count like up those 2 carbons as opposed to straight across, you have the same length chain. So it actually doesn't matter because you would get the same molecule, right? So you could just pick one or the other. I'll go straight across because I think that's easier to visualize. But just a reminder to always look for those branches. And then when we're numbering this, so we have been usually numbering left to right. So if we do that, oops. we'd have substituents on carbons 4 and 5. But if we number starting from the right side, we have substituents on carbons 3 and 4. So that is the proper way to number it to give the substituents lowest numbers. So we're going to number from the right side of the molecule. So then parent chain, we have 7 carbons, so that's heptane. On carbon 3, we have a 2 carbon substituent, that is an ethyl group. On carbon 4, we have a methyl. And on carbon 4, we have another methyl. Questions before I put it together on how I got those substituents or numbers? Okay, so now we order substituents alphabetically. Ethyl becomes before, the E comes before M, so it will be 3-ethyl. And then dash, we have 2 methyls, so we need to use the di prefix, but we still need 2 numbers. So we'll have 4, 4 dimethyl, and then heptane. Notice that the D in di, doesn't count alphabetically. We still alphabetize based on the substituent M. Okay. Ready for the next one? Okay. Here we have a ring. We have a 6-membered ring, so that's going to be cyclohexane. As the parent chain. And then we have a methyl and an ethyl, so I'll just write those down. We need to find the numbers though. So when you're oh yeah, go ahead. Yeah.
I numbered it from left to right. So there's only 4 of those methyls, but for ethyl, you just write 5 instead of 3, and we do the same name, just 5 instead of 3.
So that is not the correct name, because when you number it, there are usually multiple, at least 2 possibilities to number the parent chain. If it's a ring, there are more possibilities. But when you number it, if you number from left to right, and the substituent numbers are higher, which is what happened here, we had 4 and 5, then compared to numbering right to left, we get 4 and 3. We pick the lower numbers, the options for lower numbers. We're going to do the same thing here. We're going to number so that these 2 substituents are on carbons 1 and 2. And then, how do we pick 1 and 2 now? We could pick 1 here and 2 here, or 1 here and 2 here. When you number carbons in a ring, you'd have to go in one direction, right? So 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. The only difference in those 2 numbers, of course, is which number gets, or which substituent gets number 1, which substituent gets number 2. The way we decide that is now alphabetically. So now we should get ethyl carbon 1 and methyl carbon 2. That's the only change. We're still having a number 1 and a number 2. So to pick number 1, we go with first alphabetical. So we'll have 1, 2, 3, 4, 5, and 6. So 1 ethyl, 2 methyl. Other questions on that one? Okay, we'll go to the last one. We have a 5-carbon chain. Now hopefully you can see, looking at the molecule, we have substituents right in the middle and then one over here. So we should number starting on the right side. So we get carbons 2 and 3 for substituents, as opposed to the left side, we'd have carbons 3 and 4. So we'll number from the right. We have a methyl on carbon 2 and a methyl on carbon 3. These are two different ways to represent methyls. Sometimes Me is written, sometimes nothing is written, sometimes a CH3 is written. Those are all just one carbon. So those are methyl groups. And then we have 3-bromo. So ordering alphabetically, we have 3-bromo, 2,3 dimethyl pentane. Yeah.
So the main priority is getting the lowest number and then alphabetical? Like you wouldn't make it so that bromine have a smaller?
Right. So, yes, first priority is lowest numbers. If by numbering in like the two different ways, or if you have a ring, you get the same numbers, same 2 numbers or same 3 numbers, whatever you're looking for, then you would give the lowest number to the first that comes alphabetical. But the first priority is getting lowest numbers overall. Okay. Now we're going to, in the future, add to our nomenclature, like how to name double bonds and triple bonds, how to name other substituents like an OH group or a nitrogen NH3 group. So that will come later, but these are like the most foundational rules that we will use. Other questions about naming? The next page is new content. Okay, then we will move on. So we're going to talk about different conformations of alkanes. So alkanes are just single bonded carbon chains. The first thing we'll do, we're going to use our model kit. So if you, actually I have them here. I have one extra in case you don't have yours, but when you pull out your model kit, take out 4 of the black pieces. Ew, one of these is dirty. Okay. So I just have one that you can look at over here. I'll need it eventually. But not at this moment. So I just took, so you both can see over here. Each of these has 2 black pieces linked together, and then 3 of the just colored spheres for atoms, and then I link those together. So these 2 each represent a carbon, and then the spheres on the outside would be hydrogens for the model that we're looking at right now. So I'm going to see if you can share. Then hopefully you can see mine in the front well enough. Okay, so this is a model of ethane. Ethane, 2 carbons, carbon to carbon bond, and then each of these spheres are hydrogens. Now, we will represent ethane as a wedge and dash structure to show the tetrahedral or 3D shape. So When you're looking at a molecule, let's say you're looking at it this way. This is going to be fun. So when you're looking at it this way, this bond would be in the plane of the paper. So because this is like flat against the paper. Same with this bond, the way that I have it right now, and this one. So all three of those we draw as straight line bonds. So just a straight line, the way that we've been drawing bonds so far. Bonds that are coming out towards you, which would be these two, those are drawn as a wedge. Looks like this, just a thicker line that's on like a long triangle. And then the ones going away are dashes. So that's how we represent the 3D shape of a molecule when we're drawing on 2D paper. So we draw carbon, carbon. So that's these two, just where the black pieces connect. The carbon on your left has a straight line bond pointing down to a hydrogen. The carbon on the right has a straight line bond pointing up. And then each of these have a wedge bond and a dash bond, so we can just draw these in. So I have this note here. Tetrahedral molecules or atoms are typically drawn with two straight line bonds, one wedge bond, and one dash bond to show its molecular shape. So usually we align two with the plane of the paper. So it'd be for like a single atom, two, and then one is a wedge, one is a dash. So I have this here. This is an image from your book. We can draw this as wedges and dashes. This is another way. So remember that single bonds can rotate. Hopefully that was covered in Gen Chem. So these are constantly rotating actually. Like in reality, they're just constantly rotating. So we can represent this molecule as a Newman projection, which is as if you take the molecule, sorry, the way they have it is like this. Take the molecule and then you look at it like this. So you're looking straight down the carbon-to-carbon bond. So that's what this is here. The carbon in front has a bond pointing up, down and to the right, down and to the left. Carbon in the back has a bond pointing down, up and to the left, and up and to the right. So that's what this is a Newman projection. So this image here is showing model kit to wedge and dash structure, and then reorienting the model kit to be looking down the carbon-to-carbon bond. And then same thing with that wedge and dash structure, and then we have the Newman projection. So the way this is drawn, we have a circle to represent, let me see. Oh yeah, it's all stated right here. Start with a circle, so that's this here. The near atom, so the atom in front, lines are drawn to show this is a carbon right in the middle. So lines to the center of the circle for the three other things bonded to that carbon. And then for the back carbon, those bonds are just on the periphery of that circle. So those are these three hydrogen atoms here. We'll get practice drawing them, but this process of drawing the circle and then lines connecting in front of the circle for front carbon, lines connecting to the edge of the circle for the back carbon, that is key for drawing the Newman projection. Another thing on this image is this theta. This is a dihedral angle. This is the angle between bonds on adjacent carbons, not the same carbon. So the way we've drawn it here, this is a 60-degree bond angle. It's the angle between these two atoms here. Or we could describe the angle between this one and this one. That's a 180-degree bond angle. This one and this one would also be 60. But we're never describing a dihedral angle of these on the same carbon. This is a tetrahedral atom, so it would be 109.5 degrees. Okay, let's see. So this is one Newman projection for ethane. Now if we twist or rotate this carbon-to-carbon bond, you could rotate the front or the back carbon. The dihedral angle between the two top carbons, we'll say, will get smaller and smaller until it's 0. And now these two atoms, or these two bonds, we say are eclipsed. They're in direct, all of these bonds are eclipsed, they're in line with each other. This is the highest energy conformation of ethane. Both of these bonds are pointing up. These are both towards you, these are both back. But drawing it as a Newman projection is the best way to see that. So we can see these two bonds are overlapping. This generates torsional strain or Pitzer strain. This is associated with bond eclipsing in almost all organic molecules. So anytime you have carbon-to-carbon bonds that can rotate, there will be a conformation where the two bonds are eclipsing. Okay, so let's draw that Newman projection with eclipsed bonds. So the way I've oriented the model kit, if we put that along the plane of the paper, carbon-to-carbon bond will be straight line, and then the two bonds pointing up will be straight line bond. Just going to draw this over here. Carbon-to-carbon, hydrogen, hydrogen. Then bond pointing down and down. We have one coming towards us, one going away from us. Now when we're drawing a Newman projection, instead of looking at the molecule like this, which is how it's drawn on the paper right now, we reorient it to look down the carbon-to-carbon bond. And here you can see those front and back bonds overlapping. But if you go from this, we need to have some perspective. The way that I do that, and the way it's shown in this image up there, is with this eye. So imagine you're looking at the carbon-to-carbon bond, and then where are things overlapping? I can draw that better. Okay, so there's our eyeball. Looking down the carbon-to-carbon bond, let's take some imagination now. Front carbon, back carbon. So just to start the Newman projection, we should draw a circle. And then let's start with the front carbon. The front carbon has a carbon to hydrogen bond pointing straight up. So we'll draw that bond from the center of the circle, pointing up. And then when you're looking at it from the perspective of the purple eye, there is a hydrogen bond pointing down and a little to the right, and one pointing down and a little to the left. So remember, it's like this. Now we're looking at it this way, so you're looking at the carbon to these three hydrogen bonds. I'll add some highlighting just for this front carbon, so we know which hydrogens we're looking at. Now when we're in eclipsed conformation, where the front and back bonds are eclipsed, then the back bonds are in the same location. So we'll draw them just next to the front hydrogens because we still need to account for all of the hydrogens there. But to show that they're eclipsed, we'll just draw them right next to those hydrogens. And remember, the bond starts at the outline of that circle for the back carbon. So this is the eclipsed conformation. This is where that dihedral angle is 0 degrees or 120 degrees. 0 degrees between overlapping carbons, or front and back, and then 120 if you're looking at the front of one and the back of another that's not already eclipsed with that one. Okay. So why are we learning about this? We're talking about carbon-to-carbon bond rotation. It happens all the time, right? It's constantly moving. It just helps us understand behavior of molecules and properties of molecules. That's one of our learning goals for the class. So one thing that we now know about ethane is that it has multiple conformations. So this is interconverted by bond twisting. These two molecules, or not these two molecules, but this molecule in a staggered orientation where bonds are not overlapping is lower energy than when they are eclipsed. So it's a property of ethane. And when we get to larger molecules on the next slide, there are even higher energy and even lower energy conformations. So this is eclipsed. What we drew up there, can't remember if the lingo is already there. It's not. This is a staggered orientation. Actually, I think that's an A. Conformation. Dihedral angle is 60 and 180 degrees. So what this is showing right here is the 60-degree bond angle. This would also be 60. And then if you compare this one to the one opposite, that would be 180. Okay, so now we have two limiting possibilities here for its conformations. That's the staggered and the eclipsed. That's the highest energy and the lowest energy, opposite. Staggered is lowest energy, eclipsed is highest energy. So you can plot that on an energy diagram. We're starting high energy, then dihedral angle shifts and we get to a low energy point, that's right here. And then continue twisting, we get to another high energy. And then continue twisting, another low, another high, another low, and then you get back to the beginning. So let's just label on here, all of these are eclipsed, the crests. They're high energy, and then the troughs are all staggered. Oh, I just remembered we have to correct something in our notes, but you can write that down in a second. Okay, the thing we have to correct, sorry to take a break from this real quick. If you go back to the first page, I switched undeck and dodeck. Undeck is for 11 carbons, dodeck is for 12. So just cross those out and rewrite the prefix for 11 and 12 carbons. let's look at another molecule, another Newman projection. I have a summary here of what we can conclude from looking at ethane. The internal rotation around carbon-to-carbon bonds happens quickly. They're just constantly rotating. Staggered conformations are more stable because we don't have the overlapping of bonds. This model kit keeps the bonds really far apart, but in reality, these bonds are very close. And so there are electrons in these bonds. All electrons are negatively charged, so when they're closer together by overlapping, there's repulsion between them, and we call that the torsional strain. Eclipse conformations, these are higher energy, and they just happen momentarily, but molecules tend toward lower energy states. So although it occurs, it is higher energy. Okay, we're going to look at butane now. So now I need that to make butane. So butane, remember how many carbons that is? 4. Okay, so I've got a 4-carbon chain here. Let's look at it the way we typically look at butane. So I got 1, 2, 3, 4. Now we're going to look down the center carbon-to-carbon bond. So we have 4 carbon-to-carbon bonds here. I'm going to look down carbons 2 and 3. So now we're focusing in on this carbon-to-carbon bond. Right now I have it as a staggered orientation. It could be eclipsed, staggered, eclipsed, staggered, eclipsed, staggered. Okay. The terminal carbons as CH3, so that's just the carbons at the end of the molecule. These 2 CH3 groups, but we'll draw out wedges and dashes for the carbons 1 and 2. And I'll put CH3 here and a CH3 here. So I have chosen, let me make sure the model aligns, to make a staggered orientation where the CH3 groups, the terminal carbons, one is pointing up and in line with the paper, one is pointing down. So now this carbon has hydrogen pointing toward you, pointing away. This carbon has the same thing. So we need a wedge and a dash for each one, and then those are 2 hydrogen atoms. So let's draw based on that. Now you could start at any orientation. You could start where these are eclipsed and both pointing up or both pointing down, or carbon on the left, the CH3 is pointing up, this one's pointing down. It doesn't really matter. You want to start in an eclipsed or staggered, which is basically the 2 options here. So let's draw a Newman projection, and then we'll rotate based on the first Newman projection to get the other possibilities with different energies. So again, let's draw that purple eye. Looking down the carbon 2 to 3 bond. And then how about we take a minute or 2 and you try drawing the Newman projection based on this wedge dash structure. So I'd start by drawing a circle and then think about the carbon in front, carbon 2. Where are those bonds pointing? And then do the back. Or if you find another method useful, that's fine. That's just what I would recommend. you to think about this wedge dash doesn't look exactly the same as the other one we did. So the Newman projection won't be the same. A big difference is the straight line bond for the front carbon here is pointing down, whereas the one we did up here, the straight line bond was pointing up. So the front carbon will have a bond pointing straight down for the butane Newman projection. I'm gonna talk through this first one. So again, you can do these without looking at the model kit, but I think to visualize it and in your mind, you should know that these are 3D molecules and this is what they look like. So we've drawn it as a wedge dash structure like this. Now to do the Newman projection, we rotate it to put this carbon in front. So the front carbon has a bond to a CH3 group pointing straight down, and then hydrogen up and to the right, hydrogen up and to the left. So just to draw that Newman projection, start with the circle. Front carbon has a bond pointing straight down to a CH3. Now when you draw the Newman projections, all atoms should be accounted for. So even if this was like a long carbon chain, then the Newman projection should have a long carbon chain there. So that is, again, I'll do highlighting for the front carbon. There's that CH3 group. And then this carbon, front carbon, looking at it this way, has a hydrogen up and to the right, hydrogen up and to the left. Now, the front and back carbons, the bonds to it, will always be in this like P sign Y shape. It might be like an upside down P sign or a normal, not upside down P sign, or it could be angled, but generally you'll have this like 120 degrees between bonds. Now, if we look at the back carbon here, in this wedge dash structure, the other CH3 group bonded to this carbon, this is our back carbon, rotated this way. The other CH3 group is directly opposite to the other CH3. So this back carbon has a bond straight up to a CH3. Now these are staggered. This molecule is drawn in a staggered orientation. So there are two remaining spots, and those are both hydrogens for that back carbon. That is hydrogen down and to the right, down and to the left. This is the wedge. What was the wedge? And this was the dash. As we draw, we will label these. So this is a staggered orientation, so let's write staggered. We'll also call this anti, because the two large groups, the two CH3 groups, are anti to each other. We couldn't say that in ethane because all substituents are hydrogens. But when we have these two large groups, if they are oriented opposite each other, or let me show it like that, these two CH3 groups are anti. Now, with that first Newman projection, and we'll go along with the model kit, we're going to draw different orientations, rotating one of these carbons 60 degrees each time. So we're going to go from this staggered to an eclipse, to another staggered, to another eclipse. And we'll continue going around. So first is an eclipse. So we're just going to take the back carbon and rotate. Let me think what this looks like to you. So I'm just going to draw a little arrow and we'll write rotate back carbon. (60°). Front carbon stays the same, so I'm not going to change anything about that. And now the structure has eclipsed bonds. Top right eclipsed hydrogen, or hydrogen is eclipsed with a CH3 group in the back of the molecule. So now we have a CH3 here, and then hydrogen's eclipsed with the others. So this is eclipsed. Let's do it again. Rotating back carbon 60 degrees. Now we've reached another staggered conformation. Again, I'm going to keep the front carbon the same. You can choose as you're drawing any rotations and conformations. You can choose to rotate either the front or the back. I chose the back for this example. If you're doing an example at home, you can rotate the front, or you can even retry this by rotating the front, and you'll get the same conformations. We'll get eclipsed and then staggered, eclipsed and staggered. Okay, so if we rotate back carbon, hold on, let's see where we started. Started like this, eclipsed, front hydrogen, back CH3, rotate 60 degrees, we get staggered again, where the two CH3s are now next to each other. And then another word here, another term, this is staggered and gauche, where we have the two large groups, the two CH3s, next to each other. There's some steric hindrance. Space between them is limited, and this is still staggered, still lower energy than eclipse, but it's higher energy than the anti-conformation. So I'm just going to write steric strain here. Makes this higher energy than eclipsed. All right, let's do it again. Another rotation of the back carbon, 60 degrees. You all draw what that looks like. I've got front carbon the same, rotating the back carbon 60 degrees. That overlaps now the two CH3 groups. Oops. So again, this is eclipsed. We don't have a word for it, but this is higher energy than the other eclipse because we have the two large groups overlapping. We have more electrons in each of these CH3 groups, more intense torsional strain, and their steric strain because we have the two large groups overlapping with each other. So this is the highest energy when the large groups are eclipsed. This is the lowest energy when the large groups are anti to each other. But just to complete, we can draw two more Newman projections. Before we get back to the original staggered anti. So we can do another staggered gauche. Where the back CH3 is down and to the left. And then, one more time gives us another eclipsed. And then one more time would get us back to staggered anti. I'm just going to write staggered anti because it is the one we started with. So first Newman projection. Okay, so for any molecule, what we did is just rotate around 360 degrees. We did 60 degrees 6 times. Each step we have a different Newman projection we can describe with different language, like staggered or eclipsed. And then for staggered, it can be gauche or anti. And then after 360 degrees, we just get back to the original. So now consider, with all of these options here, how about we... Consider where each of these fall on this energy plot. So energy increases along the y-axis, and then this is dihedral angle. We didn't label dihedral angle for each of these, but you could. But just based on where the crest and troughs are, notice that this trough is lower energy than this one, this crest is higher energy than this one. Hopefully you can plot the 6 Newman projections along this energy diagram. So we have 1, 2, 3, 4 eclipsed, although these two would be the same, and then 4 crests, which are eclipsed, and then 3 troughs, which should be staggered. So tell me, what's our lowest energy one? It'll be lowest energy on the plot. Which Newman projection is our lowest energy?
Is it the staggered anti?
Staggered anti, yeah, because we have the large groups opposite each other, they have the most amount of space. So I'll just write staggered anti for this location here. Now we talked about staggered and gauche being higher energy than staggered anti, but they're still all lower energy than the eclipse. So the other troughs are staggered gauche. And we'll end there. We'll finish this graph and continue with Newman projections on Thursday. So the exam content will end at Newman projections. We'll cover more on Thursday, but it'll be about cyclohexane. But I'll just avoid that for the quiz or for the exam.